Okay, so I'll start from the beginning. So today is the fourth problem solving session for this course, Environmental Chemistry and Microbiology. I'm Shrija Ghosh, a PMRF from IIT Kanpur. I'm here to help you clear the doubts regarding the assignment questions of this week. So this week is about chemical catalysis. So I have prepared certain questions that are related to the assignment questions in your given in your module. So I'll ask the questions, and one by one you can write your answers in the chat box, and we can have a discussion whether your answers are correct or wrong. Okay, anyone having any form of doubt in any of the questions or any other topic related to this week's session, let me know. I'll try to help you out as much as possible. So I'll quickly start with the questions now. Okay, starting with the first question: which of the following best describes a catalyst? Options are: option A catalyst remains unchanged in mass and chemical composition at the end of the reaction.
Ma'am, your voice is
Sorry.
taken cracking.
Hello. It is still cracking. Is it cracking for everybody, or could someone else confirm if it's my network or uh, can someone else confirm if it is cracking for everybody, or is it just one person? Hello. All others on the call, can somebody else confirm other than Mobani Datta? Yeah, Kavita, I am just asking if my voice is clear or not. Could you confirm?
Hello,
Hello. Yeah.
madam. Yeah, can you hear
Yeah.
me?
Yeah. Is my voice clear?
Yes, ma'am.
Okay, sure. Okay. So the question is, which of the following best describes a catalyst? Options are: option A catalyst remains unchanged in mass and chemical composition at the end of the reaction. Option B, it alters the position of the equilibrium in reversible reaction. Option C, a catalyst can initiate a reaction. Option D, a substance that increases the activation energy of the reaction. So, Kavita has already given an answer, option D. What about others? What do you think? What is the correct answer? All of you write your answers in the chat box. Okay. I have one more answer in the chat box, option C. Anyone else wants to give an answer? Okay, I have two. So I have one option D, one option C, and three option A in the chat box. The correct answer is option A, which the majority is giving. So option A, a catalyst remains unchanged in mass and chemical composition at the end of the reaction. That is the correct answer. So a catalyst is basically a chemical or a molecule that lowers the activation energy of the reaction. So if you have a reaction where a reactant R is going from R to P, in that case, when the reaction proceeds, there's an intermediate that forms that has a higher energy than both the reactants and the product. So if I have to make a uh, reaction potential diagram, just a second. Yeah. Just a second, my screen is not changing. Sorry for this technical issue. Just give me 1 minute. Yeah. So a catalyst is basically a molecule that increases or decreases the rate of the reaction by decreasing the activation energy. So it does not it cannot initiate a reaction. Reaction can be initiated by the reactants. Okay. It cannot change the position of the equilibrium will remain same. Only thing that is changed is the activation energy. So when you have a catalytic reaction, basically okay, so basically what happens is, if you have a reactant that is going to product, the reactant first forms an intermediate which is at a higher energy state than both the reactant and the product. That higher energy state, that energy difference between the reactant and the intermediate, that is called the activation energy. And that activation energy, the higher the activation energy will be, the slower the reaction will proceed, because think of it in this way, that the reaction has to now travel a longer route to reach the product. In the same place, if the activation energy is lower, then the reactant will take a smaller path to reach the product, and thus the reaction will be faster. So what catalyst does, catalyst helps to change that rate of reaction, helps the reactant to reach the product faster or slower, depending on what type of catalyst it is. It basically decreases the activation energy to increase the rate of the reaction. Okay. So catalyst, in that process, it remains unchanged in mass. There's no change in the uh, like the catalyst is not getting consumed in the reaction. It always gets regenerated to drive the reaction forward. Okay, so imagine it like a cab driver uh, who is picking you up from one place and dropping you off. The cab driver is not getting down of the car and reaching to a place. It is basically helping other person to reach from one place to another. Okay, so and then cab driver can uh, go back to the initial point and pick another person to drop to that next location. So basically the catalyst is not changing, getting consumed in the reaction. It is not changing in any form. It is getting regenerated and driving the reaction forward. Okay, so whoever answered option C, catalyst can initiate a reaction, it cannot initiate a reaction. Reaction will always be initiated by the reactants. Okay, and it does not increase the activation energy. Mostly catalyst can decrease the activation energy. Okay, moving on to the next question. To maintain the strength of H2O2, what type of catalyst are you using? Option A, positive catalyst. Option B, negative catalyst. Option C, auto catalyst. And option D, none of the above. Write your answers in the chat box. To maintain the strength of the H2O2, what type of catalysts are you going to use? Write your answer. These are theoretical questions. There is no calculation in this. I hope I am audible now. My voice is clear. Yeah, then write the answer. Okay, I have one answer in the chat box, option B. Okay, I see 4 people. Okay. Okay, so most of you are agreeing with the answer option B. That is the correct answer, negative catalyst. So H2O2 is basically a very commonly known catalyst used in the reactions. So this H2O2 gets decomposed very easily. So H2O2 will decompose into water and oxygen. Okay, so what happens is when we are using let's say we have a reaction where A is going to B. Okay, and we are using H2O2 as a catalyst. Now H2O2 is going to drive this reaction forward. It will lower the activation energy. It will help the reaction to move ahead and make B faster, uh, faster and faster. Okay, but in that process we have to maintain the H2O2 strength. Okay, we have to make sure that H2O2 is not getting decomposed into H2 and water, otherwise this reaction will not go forward. So to maintain the strength of this catalyst, we need something that can stop this decomposition to happen. Okay, to maintain the strength of H2O2, we need a molecule that can stop the decomposition. So such molecule that maintains the strength of a catalyst is called a negative catalyst. It is basically inhibiting the degradation of the catalyst. So these molecules are called negative catalysts. They are technically not catalyst, because catalysts are the molecules that increases the rate of the reaction, that helps the reaction go faster. But negative catalysts are basically the molecules that are going to protect the catalysts from getting degraded. So they are kind of inhibiting the degradation of the catalyst. Okay, Okay, so negative catalyst is going to slow down the decomposition of H2O2. What is autocatalyst used for? So autocatalyst is another category of catalyst where uh, a reactant or the product becomes the catalyst in the reaction itself. So if we have a reaction like A goes to B, what will happen? The reaction will start first and very small amount of B will form. That B will act as the catalyst in that reaction. So it will auto catalyze its own reaction. So it will catalyze, basically B will act as the catalyst and then drive the reaction. So more and more A will be converted into B, and as the concentration of B will increase, the reaction will the rate of the reaction will also keep increasing, because more B will catalyze the reaction even faster. Okay, so that is called autocatalyst, where the product itself becomes the catalyst of the reaction. Is this clear? Okay. Okay, then any other doubt in this? Okay, let's move to the next question. Which of the following is an example of an autocatalyst? So now you had the question about autocatalyst. I have already explained what autocatalyst is. Let's see which of the following is an example of an autocatalyst. Option A, finely divided iron in ammonia synthesis by Haber's process. Option B, phosphoric acid in the decomposition of H2O2. Option C, redox reaction between potassium permanganate and oxalic acid. And option D, palladium for the hydrogenation of ethylene. Which of the following is an example of an autocatalyst? Finely divided iron in ammonia synthesis by Haber's process, phosphoric acid in the decomposition of H2O2, redox reaction between potassium permanganate and oxalic acid, and palladium for the hydrogenation of ethylene. What would be the correct answer? Write your answers in the chat box. These are theoretical type questions, so you should not take much time. So I see a lot of you answering option C, redox reaction between the potassium permanganate and oxalic acid. That is the correct answer. So option C here is an example of autocatalyst. Option A and option D are the example of positive catalyst, where the finely divided iron and palladium, in case of hydrogenation reaction, both of them are acting as a catalyst, driving the reaction forward, increasing the rate of the reaction. So ammonia synthesis occurs by combining nitrogen and hydrogen. So nitrogen and hydrogen combine to form ammonia, NH3, and this iron, finely divided iron particles, they provide a surface to these nitrogen and hydrogen gases to combine together to form the ammonia. Okay, and basically it is increasing the rate of the reaction, driving the reaction forward towards the production of ammonia. Similarly, palladium also acts as a positive catalyst, where it increases the rate of the reaction and helps in the addition of hydrogen to ethylene to form ethane. Okay, the second reaction, phosphoric acid in the decomposition of H2O2, phosphoric acid is an example of negative catalyst. I explained you what is a negative catalyst in the previous question. It basically slows down the decomposition of H2O2. So phosphoric acid is an example of negative catalyst. Option C, redox reaction between potassium permanganate and oxalic acid. This is an example of autocatalyst. So the reaction is, so I've written the reaction in the ionic form, where this permanganate ion reacts with the oxalate ion to form Mn2 plus. This Mn, so when the reaction starts, a small amount of Mn2 plus forms. This Mn2 plus acts as an autocatalyst, and then uh, increases the rate of the reaction by decreasing the activation energy, and that helps the reaction to make more and more Mn2 plus. As a result, the reaction rate keeps on increasing as more and more Mn2 plus keeps on forming in the reaction. Okay, so this is an example of autocatalyst. So whoever asked me what is an autocatalyst, I hope now this is clear with an example. So in this case, Mn2 plus is basically helping the reaction to move forward by decreasing the activation energy of the reaction by increasing the rate of the reaction. Is this clear to everybody? If anybody has any doubt in this, please ask. Okay. Moving on to the next question. Question number 4. Which of the following is an example of inhibition catalyst in a chemical reaction? Which of the following is an example of an inhibition catalyst in a chemical reaction? Option A, hydrogen in the hydrogenation of alkenes. Option B, lead in the decomposition of hydrogen peroxide. Option C, sodium in the reaction of sodium with water. And option D, arsenic in the reaction of sodium sulfite with arsenic. Which of the following is an example of inhibition catalyst in a chemical reaction? Sorry. Okay, I have one answer in the chat box. What about others? All of you write your answers in the chat box and then we'll have the discussion. I can see one answer in the chat box. What about others? These are theoretical type questions. You should not take this much time in these questions. In the exam, there will be questions from all the topics, and then you will have to divide your time carefully for the numerical type questions and the theoretical questions. So in these type of questions, you should not take more than 30 seconds to answer. Okay, I have 2 option B and 1 option D. Anyone else wants to answer? Okay, the correct answer here is option B, lead in the decomposition of hydrogen peroxide. Again, inhibition catalyst is another name for negative catalyst. Lead also slows down the decomposition of hydrogen peroxide, thus preventing the decomposition and uh, providing the hydrogen peroxide to act as the catalyst in the reaction. Okay, to protect the decomposition, to protect the hydrogen peroxide from decomposing, lead is added. Okay, so option B is the correct answer for inhibition catalyst. Hydrogen in the hydrogenation reaction, hydrogen is just acting as a reactant and not a catalyst. Same goes for sodium in the reaction of sodium with water. Sodium is the reactant. Option D, arsenic in the reaction of sodium sulfite. Arsenic does act as a catalyst. We will discuss about it in one of the upcoming questions. So you will have the idea what type of catalyst arsenic is playing role in. Okay. Any doubt in this question? Let me know if you have any doubt in this question. Okay, then moving on to the next question. An exothermic reaction with high activation energy for the forward reaction is given by which of the diagram most appropriately? An exothermic reaction with high activation energy for the forward reaction is given by which of the following diagrams? Look at the four figures that are given and tell me which of the following diagram is showing an exothermic reaction with high activation energy. Write your answers in the chat box. Okay, I see two option D and one option A. What about others? Anyone else wants to answer? Which of the following diagram is showing exothermic reaction with high activation energy? Anyone? Okay, so the correct answer is option D. So, two people who have answered option D, they are right. So, the first thing that we have to see is whether the reaction is exothermic or endothermic. So, what do we mean by exothermic reaction and endothermic reaction? Endothermic reaction basically means energy is absorbed in the reaction. Endothermic and exothermic. There are two terms. So, endothermic means energy is absorbed, and exothermic means energy is released. Okay, this is the fundamental difference between endothermic and exothermic reaction. Okay, so now in these two cases A and B, you see there's the reactant and this is the product. Okay, so you see the product has a higher energy than the reactant. That means there's some amount of energy that is being absorbed in the reactant and then the product is formed. The product is having higher energy. That means the reactant has absorbed some energy and then a higher energy product has formed. Okay, and this point, the top point, this is the activation energy I have been talking about. So the reactant has to reach a higher energy state which is higher than both the reactant and the product. This is the intermediate state. From this point it will again come down to form the product. So it, if it is an endothermic reaction, the product will have energy higher than the reactant. So in these two cases, the options A and B, you see the product has a higher energy than the reactant. So these two cases are examples of endothermic reactions. Okay. Whereas the options C and D, if you see, the product has a lower energy than the reactant. That means the reactant released some amount of energy to form the product, right? This is the amount of energy that the reactant released to form this product. Okay, and in this case also, if you see, this is the energy of the reactant and this is the energy of the product, and this is the energy gap between the reactant and the product. So reactant released this amount of energy to form the product. So these two examples are the examples of exothermic reactions. Okay, so our first part of the question, an exothermic reaction. So this is clear that either option C or option D will be the correct answer. Now the second part of the question says high activation energy. Now I told you activation energy is basically the transition, the difference of the reactant energy and the transition phase energy. So this is the topmost point. So here in this graph we have this. So this energy gap between the reactant and the topmost point of this graph, that is the energy of the intermediate form or energy of the transition state. So this difference in energy is called the activation energy. Now you see, for this, the transition state and the reactants have a lesser energy gap so this is not very steep. This has a lesser energy gap than this case. That's why option D is the correct answer, where the reactant and the where the reactant is having lesser higher energy than the product, showing an exothermic reaction, and the activation energy is high. For A and B, if you see, for A the activation energy is high, whereas for B the activation energy is low. Right, this is the difference in the reactant energy and the transition phase, whereas in A the difference is much larger. Okay, so if the question was an endothermic reaction with high activation energy, A would have been the correct answer. The question asked exothermic reaction with higher activation energy, so option D is the correct answer. Okay, I hope this explanation is clear to everybody. Let me know if you have any doubt in this. Anybody has any doubt? Okay, then I can move to the next question then. If anyone has any doubt, please ask. You can either unmute your mic and ask, or you can write it in the chat box, whatever is comfortable with you. I'll move to the next question meanwhile. Question number 6. Following diagram shows the energy diagram for a chemical reaction. Which of the following describes the enthalpy change? The diagram shows the energy diagram for a chemical reaction. Which of the following describes the enthalpy change? So you can see a diagram here where you have 4 points marked on the graph A, B, C and D. Now you have to tell which difference shows the enthalpy change. Is it A minus B? Is it B minus A? Is it C minus B? Or is it D minus A? Which of the following difference describes the enthalpy change? Write your answers in the chat box. All of you write the answers in the chat box. Which of the following difference describes the enthalpy change? Try to guess it depending on the explanations I have given so far. What do you think an enthalpy change could mean? Anybody? Okay, I have one answer in the chat box, option B. What about others? Nobody knows the answer, or nobody wants to answer? Okay, okay. Okay, option B, you are saying B minus A. So the explanation that I have given so far about activation energy. What do you think activation energy is? Give me that answer first. Forget about enthalpy change. What do you think activation energy would be? Mobani?
Yes, ma'am.
Yeah, what do you think activation energy would be?
Active. Ma'am, it is the minimum amount of energy which is required to initiate a chemical reaction. Uh,
Yes. So in this graph, which difference do you think is representing the activation energy? Okay. So the answer that you have given, option B, that is actually representing the activation energy, and the enthalpy change is given by option D, D minus A. So basically, what I was explaining in the previous diagram also. So this is the reactant. Okay, A is the reactant and D is the product here. Okay, and the reaction is proceeding from A to D via a reaction path where B, the maximum energy point, this is called the transition state. Okay, so I have told you so far that any reaction, when it proceeds, the reactant first achieves a higher energy state, the intermediate form, and then proceeds towards the formation of the product. Okay. So in this case also, A is first reaching this higher energy point B, which is the transition state, and then from B it is reaching the point D. Okay. So the difference between B and A, B minus A, this is the activation energy. Okay, this is called activation energy. Okay, and the difference between D minus A, D minus A is actually the enthalpy. The difference between the product energy and the reactant energy, that is called the enthalpy change. Okay. So how much enthalpy change occurred from the reactant to the product. So from the difference of the product energy and the reactant energy will give you the enthalpy change. Now tell me, in the previous question we have learned how to determine whether a reaction is exothermic or endothermic. Now answer this graph whether it is showing an endothermic reaction or exothermic reaction. I have just explained in the previous question, when do we consider a reaction? Like, just by looking at this graph you can tell whether the reaction is endothermic or exothermic. If you all understood the previous question, then you should be able to answer this, whether this graph is showing an endothermic reaction or exothermic reaction. Quickly answer. Endothermic reaction, that is correct. Why endothermic? Because the reactant energy is lower than the product energy. So now this enthalpy change, that is basically the difference between the product energy and the reactant energy, this enthalpy change, if it is positive, that is product energy is higher than the reactant energy, this enthalpy change, if it is positive, then the reaction is endothermic, and if this enthalpy change is negative, then the reaction is exothermic. Negative enthalpy change means product energy is going to be lower than the reactant energy, then only you will get uh, D minus A as negative, right? So enthalpy change, that is the final energy of the product minus the initial energy, that is the reactant's energy. If that is positive, then it is an endothermic system, otherwise it is an exothermic system. For a negative enthalpy change, it is an exothermic system. Okay, rest I have written all the things that I have explained right now, so you can go through it. Anyone has any doubt in this question or in the concept of how you see a potential energy diagram of a reaction? How do you determine whether a reaction is endothermic or exothermic? What is a transition state? So these are main key points. So whenever you see a potential energy diagram for a reaction, you should understand what is a reactant, product, activation energy, and the transition state. These four key points, and enthalpy change, five key points you should understand and you should be able to point out. Now, based on all these values, you will be able to tell, if there are multiple graphs given, you will be able to tell which reaction has a lower activation energy, which reaction has a lower enthalpy change, which is an endothermic reaction, which is an exothermic reaction, and so on. Is there any doubt in this? Please write your doubts in the chat box, or you can unmute and ask whichever way you feel comfortable. But please interact. This is a doubt clearing session. It won't make sense if you will not ask any doubt. You have to understand the concepts. The point of joining this session is basically to understand the concept. If there's any small doubt remaining in any of the concept, this is the time you have to ask. Okay. If there's no doubt, then I'll move ahead to the next question. Question number 7. Which of the following is an example of an induced catalyst in a chemical reaction? Which of the following is an example of an induced catalyst? Option A, hydrogen in hydrogenation of alkenes. Option B, lead in the decomposition of hydrogen peroxide. Option C, sodium in the reaction of sodium with water. And option D, arsenic in the reaction of sodium sulfite with arsenic. So till now we have studied negative catalyst and positive catalyst and autocatalyst. Now this is another term called induced catalyst. So write your answers in the chat box, and then I'll explain what induced catalyst is and how the particular option is acting as an induced catalyst. I see 3 people have answered option D. What about others? I can see 17 people have joined the meeting. What about others? Why everyone is not giving their answers? Okay, so option D is the correct answer, arsenic in the reaction of sodium sulfite with arsenic. So, like autocatalyst, induced catalyst is also something that is forming in the reaction that is acting as a catalyst. But the difference between autocatalyst and induced catalyst is in case of autocatalyst, the product itself acts as the catalyst and drives the reaction so that more and more product is formed. Okay, but in this case, in case of induced catalyst, one of the reactant will have a catalyst role and one of the reactant will keep on forming more and more product. So in this case, in this example, sodium sulfite is getting oxidized to sodium sulfate, and we have arsenic in form of oxidation state 3. So arsenic can exist in two oxidation states, arsenic 3 and arsenic 5, plus 3 and plus 5 oxidation states. Okay, so initially when the reaction starts, small amount of arsenic 3 is oxidized to form arsenic 5 by the oxidizing agent. By in presence of oxygen, arsenic 3 will convert into arsenic 5. This arsenic 5 will now have the catalytic role. It will accelerate the oxidation of sodium sulfite. So more and more sodium sulfite will form sodium sulfate, and in that redox reaction, arsenic 5 will get converted back to arsenic 3. So this arsenic 3 and arsenic 5 redox pair, they will act as a catalytic cycle. So arsenic 3 will again get converted into arsenic 5, that will drive the oxidation of sodium sulfide to sodium sulfate, again get converting back to arsenic 3. So arsenic 3 and arsenic 5 will keep on going in cycles to drive more and more sodium sulfite oxidation. Okay, is this clear? So this is an example of induced catalyst. Is this clear to everybody? If you have doubt, you can ask, I can explain again. Anybody has any doubt? Okay. Okay, then moving on to the next question. Question number 8. In homogeneous catalysis, the catalyst, option A, exists in the same phase as the reactant. Option B, exists in the different phase from the reactants. Option C, it is consumed during the reaction. Option D, it acts as an inhibitor of the reaction. In homogeneous catalysis, the catalyst exists in the same phase as the reaction, exists in a different phase from the reaction, is consumed during the reaction, or it acts as an inhibitor of the reaction. What would be the correct answer? What is homogeneous catalysis? I see most of you have written option A, exists in the same phase as the reactant. That is the correct answer. So by the name homogeneous, you can understand that all the components of the reaction are in the same phase. So if the reactants are in gaseous phase, the catalyst is also going to be a gas. Or if the reactant is in solid phase, then the catalyst is also going to be a solid. So that is an example of homogeneous catalysis, where the catalysts are in the same phase as the reactants. Okay, so the example of this kind of catalyst uh, is given by the Chambers process of sulfuric acid synthesis, where nitrogen oxide acts as the catalyst. So sulfur dioxide combines with oxygen to form uh, sulfur dioxide combines with oxygen here, and nitrogen oxide acts as the catalyst in this reaction. So if you see in this reaction, nitrogen oxide is also present in gaseous form, sulfur dioxide and oxygen are also present in gaseous form. So all the reactants and the catalysts are present in the same phase, that is the gaseous phase. Okay, so this is an example of a homogeneous catalyst, homogeneous catalytic reaction, or homogeneous catalyst. Okay, moving to the next question. Paul Anastas and John Warner developed 12 principles of green chemistry in 2000. Which statements among the following is or are true? Option A, analyze processes in real time. Option B, use renewable feedstock. Option C, prevent waste. And option D, all of the above. Okay. I see 3 answers in the chat box. Option D, all of the above. That is the correct answer. So, there are 12 principles of green chemistry. It was originally developed by Paul Anastas and John Warner in 2000. And the principles are: first is prevent waste. Second is design safer chemicals and products. Third is design less hazardous chemical synthesis. Fourth is use renewable feedstock. Fifth is use catalysts. Sixth is avoid chemical derivatives. Seventh is maximize atom economy. Eighth is use safer solvents and reaction conditions. Ninth is increase energy efficiency. 10th is design chemicals and products to degrade after use. 11th is analyze processes in real time to prevent pollution. And 12th is minimize the potential for accidents. So these 12 principles, basically by the name itself, you can understand green chemistry means that your reactions and the processes that you are doing in chemistry, they should be sustainable, they should be renewable, they should be environment friendly. So there were certain principles that were developed to encourage people to towards green chemistry. Okay. Okay, moving to the next question. Which of the following is an example of heterogeneous catalysis? Option A, enzyme used in biological processes. Option B, hydrogenation of alkenes using platinum on solid support. Option C, trans esterification of fatty acid triglyceride with methanol. Option D, acid catalysis in solution. Which of the following is an example of heterogeneous catalysis? So we have discussed homogeneous catalysis, so you should understand now what heterogeneous catalysis is. Option A, enzyme used in biological process. Option B, hydrogenation of alkenes using platinum on solid support. Option C, transesterification of fatty acid triglyceride with methanol. And option D, acid catalysis in solution. I see only one answer in the chat box. What about others? All of you write the answers in the chat box. Okay. I see 4 of you have answered option B, hydrogenation of alkenes using platinum on solid support. That is the correct answer. Option B is the correct answer, hydrogenation of alkenes using platinum on solid support. So here platinum is the catalyst and alkenes like ethylene is hydrogenated by addition of hydrogens to form alkanes. So example is the conversion of ethylene to ethane. So platinum is used as a solid support. On the platinum, the gas molecule, the hydrogen gas molecule, they will get adsorbed and they will uh, split into hydrogen atom, dissociate into individual hydrogen atoms. So H2 will dissociate into H atoms, and these H atoms, they will add sequentially to the ethylene molecule to form ethane, and then ethane gets desorbed from the platinum surface so that the surface is regenerated for new hydrogen atoms to add. So basically, so this is your ethene or ethylene molecule, and ethane would be with 3 hydrogens, right? So there are addition of 2 hydrogen molecules in this carbon and this carbon, and the double bond becomes single bond. Now this addition of hydrogen, so there's a platinum support. So platinum is added in the solid form. All these reactants are in gaseous form. Okay, so this is a gas and hydrogen is a gas. So H2 will dissociate on the platinum support into individual hydrogen atoms, and then it will get added onto this ethylene molecule sequentially for this molecule to form, and once this molecule forms, that will get dissociated from the platinum, and then the platinum surface will be free for new hydrogen atoms to get attached and then for the reaction to proceed. So platinum is not getting consumed in the reaction, so it is acting as a catalyst. It is providing a surface. It is in a different phase than the reactant. Reactant is in gaseous phase, whereas the catalyst is in solid phase. So it's a heterogeneous catalyst. Okay, and it is driving the reaction forward. It is a positive catalyst. Okay, so till now, whatever concepts we have discussed about catalyst, I hope all of them are clear in this question. If anybody has any doubt in this, please ask. Okay. Moving on to the next question then. Which theory gives a proper explanation on the mechanism of heterogeneous catalysis? Which theory gives a proper explanation on the mechanism of heterogeneous catalysis? Option A, absorption. Option B, adsorption. Option C, both of the above. And option D, none of the above. So I just explained you an example of heterogeneous catalysis. So think of that example and tell me which of the following uh, could explain that mechanism of heterogeneous catalysis. Write your answers in the chat box quickly, all of you. Okay, I see 4 answers. All of them are option B, adsorption. That is the correct answer. So, the example that I gave about the platinum being the solid support where hydrogen is getting attached. Hydrogen attachment is basically a process of adsorption. Hydrogen gas is getting adsorbed by the platinum support, getting dissociated on the platinum support, and after addition to ethylene, the ethane is getting desorbed from the platinum. Okay, so there's adsorption of hydrogen and desorption of the product. Okay, so adsorption is the explanation for heterogeneous catalysis. It is the mechanism. Adsorption is the mechanism for the heterogeneous catalysis. I hope that's clear to everybody. Moving to the next question. In the reaction of the hydrogen peroxide decomposition, the presence of manganese oxide, option A, acts as a negative catalyst to slow down the reaction. Option B, increases the rate of decomposition significantly. Option C, changes the equilibrium position of the reaction. And option D, does not affect the reaction. In the reaction of hydrogen peroxide decomposition, in the presence of MnO2, what does presence of MnO2 how MnO2 affects the decomposition of H2O2? Write your answers in the chat box. What is the role of MnO2 in H2O2 decomposition? Options are option A, acts as negative catalyst to slow down the reaction. Option B, increases the rate of the decomposition. Option C, changes the equilibrium position of the reaction. And option D, does not affect the reaction. Okay, I see 4 of you have answered option B, increases the rate of decomposition significantly. That is the correct answer. So, till now we have been talking about negative catalysts which were added to slow down the decomposition of H2O2. But in the reaction where you want to decompose H2O2, in such cases, MnO2 is added, which acts as a positive catalyst. It increases the rate of decomposition significantly. So, how does it act as a catalyst? Basically, it follows the same mechanism as the platinum in the hydrogenation reaction. So manganese dioxide is also added in a solid state. This is also an example of heterogeneous catalysis. And MnO2 increases the rate of the decomposition by providing a surface on which hydrogen peroxide is in liquid state, okay, and MnO2 is in solid state. So MnO2 provides a surface on which hydrogen peroxide molecules can break apart easily, lowering the activation energy of the reaction. So this speeds up the formation of oxygen gas and water, but does not get consumed in the process. So MnO2 does not get consumed in the process. That means MnO2 acts as a catalyst, and because it is increasing the rate of the reaction, it is acting as a positive catalyst. Okay. So the reaction H2O2 breaking down into H2O and oxygen gas. This reaction is actually catalyzed by presence of MnO2. When MnO2 is present, hydrogen peroxide can get adsorbed on the MnO2 surface and break down easily. Okay, the surface area basically gets increased. Is this clear? If anyone has any doubt, please let me know. Okay. Moving to the next question. Turnover number refers to. What is turnover number? Options are: option A, the number of active site in a catalyst; option B, the number of substrate molecules converted per unit time; option C, the total number of reactant molecules converted per catalyst molecule before deactivation; and option D, ratio of reactant to product concentration. Which of the following defines turnover number? Write your answers in the chat box. Anyone else wants to write the answer? Again, I have only 4 answers. What about others? Anyone else? Okay, 4 of you have answered option D, option B. That is number of substrate molecules converted per unit time. So all of you are in like giving incorrect answer actually. The correct answer here is option C. So there are two terms, turnover number and turnover frequency. Okay, so when we are talking about turnover number, it is basically the number of molecules getting converted by one catalyst molecule. So per catalyst molecule, so one catalyst molecule converting how many reactant molecules, that is defined by the turnover number. So let's say one catalyst molecule can convert three reactant molecules before getting deactivated. So catalysts also have a lifetime. Although they keep getting regenerated, still they after performing certain number of catalytic cycles, they get deactivated. Okay, so before deactivation, how many reactant molecules, how many catalytic cycles it can turn over. Okay, so that is the turnover number. Okay, so how many catalytic cycles it can perform? One catalyst molecule can convert how many reactant molecules? That is defined by the turnover number. So the correct answer is option C, total number of reactant molecules converted per catalyst molecule before deactivation. Okay. So option B, that is number of substrates converted per unit time, that is not the turnover number. Turnover number does not have anything to do with time. Turnover number basically is the number of molecules converted by the catalyst before deactivation, by one catalyst molecule before deactivation. Okay, number of molecules, reactant molecules per catalyst molecule before deactivation, that is the turnover number. It has nothing to do with the time. Okay, is this clear? All of you who have answered option B, is this clear to you now?
Yes, ma'am.
Okay, great. The next question is turnover frequency is defined as. So here you will understand the mistake that you made in the previous question. So turnover frequency is defined as, options are number of catalytic cycles per active site per unit time. Option B, total number of molecules a catalyst can process. Option C, time taken for a catalyst to get deactivated. And option D, ratio of activation energy to reaction time. Which of the following is the correct answer here? What is turnover frequency? Now answer this. Now you have understood what is turnover number. So tell me what is turnover frequency. Write your answers in the chat box. I see only 2 answers in the chat box. What about others? All of you write your answers in the chat box. What is turnover frequency? Okay. So 2 of you who have answered option A as the correct answer. That is right. Number of catalytic cycles per active site per unit time, that is the turnover frequency. So turnover frequency is basically the turnover number per unit time. Okay. So in these options, okay, tell me one more thing. Which of the following options are defining turnover number here? If you understood the previous question, you should be able to answer. Which of the following options are showing is defining turnover number? One of the option is defining turnover number. Tell me which option is defining turnover number here. At least answer this. All of you should answer this. I have already explained in the previous question, right? Yeah, so option B defines the turnover number. So if you divide turnover number with time, you will get the turnover frequency. Like how many number of molecules are catalyzed by one catalyst in uh, per unit time, in 1 unit of time. So if you are taking time in second, so in 1 second, how many molecules are getting converted into product by one catalyst molecule? Okay, so per active site per unit time, or per catalyst molecule per unit time. Okay, so total number of molecules a catalyst can process is the turnover number. Per unit time would be turnover frequency. Is this clear to everybody? What is turnover number and turnover frequency? These two things are very important, because now I am going to ask certain numericals where you have to use this concept and solve the answer. Okay. So I hope this is clear to everybody. If anybody has any doubt in turnover number and frequency, ask now. Okay, moving to the next question. 25 mg per liter of textile dye X is completely degraded catalytically. The catalyst was used at a dose of 0.5 grams per liter and the time taken was 2 hours. Calculate the turnover frequency of the catalyst. So you have the amount of textile dye, that is the reactant here, that is getting degraded by using a catalyst. The amount of reactant is given, amount of catalyst is given, time taken for the reaction is given. You have to calculate the turnover frequency. How will you calculate that? I'll give you some time. All of you use your notebooks and do the calculation and give me the answer. Let's see if you can get the correct answer or not. Write your answers in the chat box. Does anyone know how to solve this? So what is turnover frequency? It is the number of reactant molecules catalyzed per unit per catalyst molecule per unit time. So first you have to find the number of reactant molecules. How will you find that? Are you solving this? Is anyone able to land on an answer? Okay, I see 2 people answering option C. What about others? Anyone else solved it? Okay, first, how will we calculate the number of molecules, reactant molecules? Tell me that. Okay, 2 of you who have answered option C, how did you calculate the number of molecules?
Ma'am, can I say?
Yeah, sure.
Ma'am, for the number of molecules, 25 milligram per liter, so it will be 25 into 10 to the power minus 3 liter
Yes.
into 6.023 into 10 to the power 23
Yes.
divided by the molecular weight, which is 408.
Yes, that is correct. So basically, you have the concentration given of the reactant given. So 25 milligrams per liter, and your catalyst is also given as 0.5 grams per liter. So 25 milligrams would be 25 into 10 raised power of minus 3 grams in 1 liter. Now that is the mass. You have to find the moles first. Okay, so to calculate the moles from mass, you divide it by molecular weight. So 25 into 10 raised power minus 3 divided by 408, that will give you the number of moles. Now, if you recall from your previous chemistry knowledge, you will remember that 1 mole of substance has 6.023 into 10 raised power of 23 molecules. That is the Avogadro number. So if 1 mole has 6.023 into 10 raised power 23, then 25 into 10 raised power minus 3 divided by 408 moles will have that many moles multiplied by 6.02 into 10 raised power of 23 molecules. So that would be the number of molecules. Number of molecules now divided by the catalyst, that is 0.5, and then divided by the time, that is 2 hours. Now the options are given in seconds, so convert 2 hour into seconds. So 2 into 60 into 60, that would be 3600. Okay, so 3600 into 2, that would be 7200. So now do the calculation and tell me the answer. Are you getting option C as the correct answer, or is it something else? None of you,
Yes, ma'am, option
other than
C.
other than 2 of you, none of you are able to solve this. What about others? Are you also getting option C as the correct answer? So 25 into 10 raised to the power minus 3 into 6.023 into 10 raised to the power 23 divided by 408. This is the number of molecules per liter. Dose of catalyst is given as 0.5 grams per liter and time taken is 7200 seconds. So turnover frequency would be number of molecules divided by the catalyst dose divided by the time. So all of these things are in the denominator, and when you solve this whole thing, you will get the answer, that is the turnover frequency. So molecules per gram as in per gram of catalyst per second, because per unit time is giving you the frequency. If you don't divide it by time, what will you get? You will get the turnover number. Okay, I hope this is clear to everybody. If you have any doubt, anyone, if you have any doubt, please let me know in the chat box or unmute and ask. I'll move to the next question. If a catalyst converts 500 molecules of reactants before deactivation and the reaction runs for 50 seconds, what is the turnover frequency? So, if a catalyst converts 500 molecules of reactant before deactivation and the reaction runs for 50 seconds, what is the turnover frequency? Options are 10, 50, 5 and 100. What would be the turnover frequency here? This is a very simple question. You don't even need a calculator. Quickly answer. Read the question carefully. You will understand the question and you will be able to answer. I already see people answering in the chat box. Yes, option A. 4 of you have answered option A. Very good. That is the correct answer. So, a catalyst converts 500 molecules of reactant before deactivation. This statement, what does it mean? 500 molecule is the turnover number, right? Because one catalyst converting the number of reactant molecules before deactivation is the turnover number. So that means 500 molecule is the turnover number here, and the reaction time is given as 50 seconds. So your turnover frequency would be turnover number per unit time, right? So 500 divided by 50, that is 10 per second. Okay, so 10 molecules per second would be the turnover frequency. Is this clear to everybody? All of you who haven't answered or who are not answering at all, is it clear? Are you understanding this? So catalyst converting 500 molecules of reactants before deactivation. That means 500 molecule is the turnover number, and we have to calculate the turnover frequency. Reaction time is given, so turnover number divided by the time would be turnover frequency. Okay, so 500 divided by 50 would be 10. Okay, so this is very simple calculation. So I hope this is clear to everybody. Yes, do you have any question? Okay, moving on to the next question. If a molecule M having concentration of 100 micromolar is reduced completely in the presence of a catalyst at a dose of 1 gram per liter, then calculate the turnover number of the catalyst. So here you have to calculate the turnover number. You have the concentration of the reactant and the catalyst dose. So you have to calculate the turnover number of the catalyst. Just make sure you see the units carefully and then solve your answer. Quickly calculate and let me know the answer. Yes, I already have an answer in the chat box. What about others? Yes, I have 3 people answering option C, 6.0 into 10 raised power 19. That is the correct answer. So basically, in the previous question, we had the concentration in milligrams per liter. In this question, we have the concentration in molarity form. So micromolar means micromoles per liter. So we already know the moles. So the molecular weight given here is of no use. 100 micromolar means 100 micromoles per liter. So in 1 liter, 100 micromoles of reactants are there and 1 gram of catalyst is there. So 100 micromoles means 100 into 10 raised to power of minus 6 into 6.02 into 10 raised to power of 23 molecules in divided by 1 gram, because catalyst dose is 1 gram per liter. So that means in 1 liter we have 6.02 into 10 raised to power of 19 molecules, and we'll divide that with 1 gram. So we'll get 6.02 into 10 raised to power of 19 molecules per gram as the turnover number of that catalyst. Is this clear? So we have sorry, there's some, I'll change this editing. And so number of molecule is basically 100 into 10 raised to power of minus 6. This should be in power, into 6.02 into 10 raised to power of 23. 23 is in power, and here you can see, and then this is divided by 1 gram per liter. Is this clear? Is this clear to everybody? People who haven't answered, tell me if you have any doubt. The concept of turnover number, turnover frequency, this should be clear first. Then only you will be able to solve the questions, solve the numericals. Okay. Moving to the next question. Why is a high turnover frequency desirable for catalysis, or desirable in catalysis? Option A, it indicates that catalyst is unstable. Option B, it means that catalyst is highly efficient. Option C, it reduces the activation energy. And option D, it ensures the catalyst remains in reaction indefinitely. Why is a high turnover frequency desirable in catalysis? Why do we want high turnover frequency from a catalyst? Write your answers in the chat box. I have one answer. What about others? Okay. So 3 people have answered option B. It means the catalyst is highly efficient. That is the correct answer. So turnover frequency, I explained, it is the number of reactant molecules converted by one catalyst molecule per second. Okay. So it basically tells you how many times one catalyst molecule can convert the reactant molecule into product. So that is basically telling you the efficiency of that catalyst. So high turnover frequency will mean high efficiency of the catalyst, meaning that it processes more reactant molecules in a shorter time. Okay, so if in 1 second one catalyst can convert 10 reactant molecules and other catalyst can only convert 5 reactant molecules, that means in a shorter time we will have more amount of product or more number of reactant molecules converted into product by the first category of catalyst than the second, because the first category had a higher turnover frequency, meaning it has a higher catalytic efficiency. Is this clear? If anyone has any doubt, please let me know. Moving to the next question. Detergent and soap in water has some common properties. Both of them are option A, biodegradable in nature, option B, small hydrophobic molecules, option C, suitable for decreasing the surface tension of water, and option D, suitable for increasing the surface tension of water. Detergent and soap has some common properties. What are the property that what is the property that is common between detergent and soap? Write your answers in the chat box. I see two answers. Suitable for decreasing that surface tension of the water. Option C. Yes, that is the correct answer. So, both detergent and soaps, they are surfactants. They are called surfactants, and surfactant molecules decrease the surface tension of the water. Okay. So, both of them have this property in common, that they are suitable for decreasing the surface tension of water. Okay. Next question is sodium dodecyl sulfate is option A, a cationic surfactant, option B, an anionic surfactant, option C, a zwitterionic surfactant, and option D, non-ionic surfactant. Sodium dodecyl sulfate, commonly known as SDS, it is a cationic surfactant, anionic surfactant, zwitterionic surfactant, or non-ionic surfactant. Okay, I see 4 people have answered option B, an anionic surfactant. That is the correct answer. So, sodium dodecyl sulfate, this is basically a detergent and it is an anionic surfactant. This is the structure of the surfactant where you have a long hydrophobic tail and a polar head group. So, yeah. So here you can see the molecule has a polar head group and a long hydrophobic tail. This hydrophobic tail will basically it will not get soluble in water, and this polar head group, it will interact with the water molecule. So when you dissolve a detergent in water, what happens is the polar head group, they will form a outer uh, covering, and the hydrophobic tails will be buried inside, and thus the detergent molecules will get solubilized in the water. And this particular detergent, sodium dodecyl sulfate, it is called anionic surfactant because the polar head group is negatively charged. So that's why it is called the anionic surfactant. Okay. Is this clear to everyone? So basically these detergent molecules, they form a structure called micelles. So these hydrophobic tails, they are buried inside the inside those micelles. Micelles are circular structures where the circumference of the circle is formed by the polar head groups, and the hydrophobic tails, they are buried inside the micelles, and these micelles are then uh, these micelle formation occurs for so that these detergent molecules can stay in the hydrophilic environment, because in itself it is not it has both the hydrophobic tail and the hydrophilic head group, right? So only hydrophilic part can interact with the water, So for that, the hydrophobic part gets all of them come together and form a circular structure where the hydrophilic part is towards the outer surface of the structure, so that it can interact with the water molecules, and the hydrophobic part does not have to interact with the water molecules. So that is called a micelle. These detergents have a property to form these micelles, and there's a concentration for each detergent that is determined, that is called the critical micellar concentration. So above that particular concentration only, that particular detergent will form the micelles. Okay, is this clear? So this is the last question of the session. If you have any doubt, let me know. Do you have any doubt? Anyone wants to ask any other question related to these this session's topic? Hello, am I audible? Okay, do you want to ask any question? Anyone? Is everything clear in today's session?
Yes, ma'am, it's clear.
Okay, great then. Then
Yes,
I'll
ma'am.
end. Then I'll end this session today. Thank you so much for joining. I'll
Thank you,
see you
ma'am.
next Tuesday for the next session. Okay. Thank you all for joining. Bye bye.